Welcome to the downstream processing in biotechnology and bioseparation class. In this lecture, we will talk about the extraction. And previously, we talked about the filtration, centrifugation, and cell disruption. After we separate the solids of the liquid mixture, and then we get the liquid, and then we would like to separate some solute from the solvent or a desired product from a mixture in liquid phase. The most common to the first step, we will consider like the extraction. In extraction, we can classify into type of extraction is liquid extraction and solid liquid extraction. In this part, we talk and we will focus on the liquid extraction. The extraction process taken as small takeoff the partitioning of solute between immiscible liquid phase. In this case, if we would like to separate some solute that dissolve in solvent, for example, we have some like penicillin dissolved in water, for example. Okay, we have to choose another solvent that dissolve easier in penicillin than water. For example, we should write amino acetate. For this case, at pH 5.5, amino acetate is dissolved easier in penicillin, or penicillin can dissolve in amino acetate than water. In this case, we use amino acetate to separate penicillin from water. And then for this case, we can separate amino acetate or penicillin by titration or another technique that is easier to operate. Like this. Another example, right? Citric acid. Right? Citric acid, we can use citric acid to separate. Sorry, we can use like methyl amyl ketone. Methyl amyl ketone. Yes. Initially, we have the mixture of citric acid in the water. In the process of citric acid production, where produced by the fermentation. After the fermentation reaction, we get like some the mixture. After we separate solid, we get the liquid phase. In the liquid phase, we have like most of water, and also the desired product, citric acid, mixed with water. For this case, we would like to separate citric acid. In this case, in the case of extraction, we can choose methyl amyl ketone. That's like to separate the citric from water, because at pH 4, for example, right, at pH 4, citric acid can dissolve in methyl amyl ketone. That's right. More soluble or more dissolved in methyl amyl ketone than in water. That's it. We can use the methyl amyl ketone to separate the citric acid from water. That's right. For this case, like for these two examples, right, the solute concentration increase in the first liquid phase as a result of depletion from the second phase. Right. The first, we have the solute and solvent mixed together, and then we add a new solvent to separate solute, right, because we call this is an extraction process. Okay. Why we can separate by the extraction process? The first term that we use to determine which we can separate or not, that we call the partition coefficient. Partition coefficient is expressed as X divided by Y, where X is the solute concentration in the light phase or light liquid phase. We represent by L, and Y is the solute concentration in the FL phase, which represent by S. In many cases, the light phase will be an organic solvent and heavy phase will be water. Mostly in bioprocess, like we separate the mixture from the fermentation board. Like water is the most component in our mixture. We consider water as the heavy phase. And another solvent that we would like to use to separate the solute, we call it the light phase. Mostly we use the organic solvent. That's right. Okay. In often, the value of K will be constant, independent of solute concentration. That's right. reflect that the fact that most biochemical extraction take place in dilute solution. Okay. In mostly we can classify the extraction, liquid extraction in three types. The first one is extraction solvent system, which is aqueous, non-aqueous system. Aqueous, non-aqueous system. For example, we would like to separate citric acid from water by a methylamine, something like it. For this case, initially we have aqueous solution, like citric acid dissolved in water. We call it aqueous solution. And then we add organic solvent. This is non-aqueous solution. So we have two systems. Initially, we have aqueous system, water and citric acid. And the second system is organic solvent. We mix together. We call this aqueous, non-aqueous system. And the second one is aqueous two-phase. Aqueous two-phase means we have the first one is aqueous system, and the second one is also aqueous system. What does it mean? For example, if we would like to separate citric acid, let's mix in water. For this case, we add some organic solvent that also dissolve in water. In this case, the second system also dissolve in water and mix together. And the last one, because it's supercritical fluid extraction. We use a supercritical fluid at the extraction to separate. Okay, for the most ideal liquid extraction, do not react with solute. Do not react with solute. Non-denaturing, non-toxic, inexpensive, immiscible with the feed. Provide a large distribution coefficient or K value. For this product. This is important. The extraction should be non-toxic, inexpensive. Okay, this is for the important property of the extraction that we use to separate some solutes. And also the different intensity between two phase should be large enough to promote the phase separation. After we mix this system together, and finally we have to separate by the phase separation. The heavy phase should be at the bottom and light phase should be the top. So it's easy to separate for the next step. And also the interfacial tension should not be so high. If the interfacial tension is so high, that means we need energy. We need energy for surface and contact time is high energy for that case. But also the interfacial tension should not be so low also, because if the low interfacial energy is maybe the emulsion formation, the formation of emulsion. That's in the problem of separation. For that case, if we have interfacial energy is high, so high or so low, we can solve this problem by using the centrifugal extractor. That for this case, we extraction also, but mix between extraction and centrifugation. Then for centrifugal extractor can overcome this problem, the different intensity and emulsion formation. For this case. Okay. This table will show you an example of advantage and disadvantage of the solvent system, aqueous, non-aqueous system, aqueous two-phase system, and supercritical fluid extraction. Mostly when we utilize the aqueous, non-aqueous system, we can use organic solvent. So we can use organic solvent, and the vapor pressure of solvent is higher than water. Heat of vaporization of solvent is lower than water. That's right. We get the larger and we get some pure crystal form. That's right. And also inorganic salt remain in the water. This is the advantage. But maybe the disadvantage, right? We have some biopolymer. That's right. The denatured inorganic solvent, and sometimes expensive, and some organic solvent is flammability and toxicity, something like that. And also there are some waste. That's right. Too many. It is the disadvantage for the aqueous, non-aqueous organic solvent. And this is for example of extraction. We can use carboxylic acid, amino acid, alcohol, steroid, something like this. And also for the advantage for aqueous two-phase. That's right. Aqueous two-phase is, for this case, it can preserve the biopolymer activity. That's right. It can help to eliminate the disadvantage of the solvent for that case. But the disadvantage that is maybe inexpensive. Sorry, expensive for pure reaction polymer. Maybe small phase density different. And it is the important disadvantage that there are some small difference in density between heavy phase and light phase. The attraction for this is in aqueous two-phase system, that's protein, enzyme, that's like something like this. And the last one is supercritical field attraction. Supercritical attraction, the advantage is as a solid penetration and so use this solution. CO2 solvent, if we use the CO2 solvent, is non-toxic and easy to remove. But the disadvantage are high cost, because the high pressure equipment and high compression this indicate a high cost also. And also for this case, we need experimental determination of process condition before to the large scale need the disadvantage. The attraction for this system, like example, unauthorized therapeutic food beverage processing, like for example. And this table show you some example of the K value of partition coefficient for some bioproduct. For example, ethanol and N-butanol. For this case, if we use octanol as the solvent to extract ethanol and butanol, can be seen at 25 degrees Celsius. This K value show that the octanol is better for butanol and water synthesis. That's why we can use octanol to separate N-butanol or normal butanol is easier than ethanol because K value is higher than ethanol or butanol. This, for example. And like amino acid, you can get the amino acid, mostly the value of K is very low value. It's hard to separate amino acid by the organic solvent system. That's an organic solvent system because the K value is very low. It's lower than 0. That's lower than 1. Sorry, it's lower than 0.01, 0.02. It's quite low value. This for example. And this for another example, like antibiotic and protein. For this case, it also depends on temperature and pH. Like antibiotic, it's also pH. The K value is very high. For example, like penicillin F. If we use the penicillin F, we use the solvent at amyostate. We would like to separate separate penicillin F by using amyostate at pH 4 and pH 6. It's different K value. For this case, at higher P value, it's hard to separate penicillin A. At pH 6, we get K value is very low value, 0.06. And at pH 4, we can see that the K value is very high, like 32, that we can easily to separate at pH is low. This, for example, for the system of the organic solvent system. Okay, for the case for the basic equation in the theory of the solvent extraction, For this case, we example, we have two systems. The solute dissolved in water, we call this aqueous solution. And solvent, pure solvent, or it may be included some water in the solvent also. Add to the mixture of water and solute. We consider this system. Mostly at the equilibrium state. At the equilibrium state, we talk about the chemical potential. The chemical potential. The chemical potential at equilibrium state of heavy phase equal to liquid phase. And also you can express the chemical potential in terms of standard condition like mu0 of heavy phase equal to RT log Y equal to mu0 of light phase plus RT log X. That's right. And therefore you can rearrange this equation. You can write X over Y equal to K with this exponential of mu0 heavy phase minus mu0 of light phase divided by RT. You can use this equation to estimate the K value by the theoretical side, and also the K value that's increased with decreasing pH for antibiotic, like we show you in the previous table. The K value also can be estimated by the previous equation, and also we can express for the K value in terms of molar volume, solubility parameter, as like for the live phase or laffinate phase. We call the live phase or extract phase. Sometimes we call it live phase or the extract phase. And heavy phase or heavy solvent or raffinate phase. L, S, and solute as A for this case. And then from previous equation, if we take log both sides, we get log K equal to mu 0 heavy phase, and not mu 0 light phase, divided by H. In this case, we can express in terms of the partial molar volume and solubility parameter, like this equation 5. The solubility parameter, you can find this in table 5, table 8.9. This show you like the solubility parameter for common solvent, like aminoacids is S, like chloroform is 9.2, for example. That's get from this equation. This equation show that the similar solubility parameter between the biological species to be attract and increase the partition coefficient. Increase the partition coefficient. We increase the solubility parameter. Partition coefficient also increase in this case. Okay, and another system, if we add some organic solvent, and also it can be like to ionize to be the ion and ion also with the ion in some bioproduct. If some bioproduct dissolved in water, it can be ionized to positive charge, negative charge, or no charge, something like this. If we would like to some solvent, organic solvent, to separate this ionic charge, sometimes it's difficult to separate because the organic solvent is no charge. For this case, we can use the agent or ionic pair agent, that's ionic pair agent, to solve this problem. For ideal ionic pair agent of water soluble when ionized, that's why we can add some ion pair agent. That's why add some ion pair agent to our system, and then it can be easily to isolate to return the desired species. So, because like in our system, we have bioproduct that can ionize in water if we add some solvent to the system, but solvent cannot ionize. For this case, we can increase or we can improve the attraction efficiency by add some ion pair agent, something like this, ion pair agent. Right. For example, that's like for this case, we like acetate or butyrate organic solubility exceed that of acetate. The ion pair in with the cationic biopolymer. That's right. Like the quaternary amide like chaltropic tetrabutane and hexadecyl-tributyl ion pair. That's right. For this case, it's February with an ionic biopolymer at IPA. For this, we can add some this and some this to our solution. That's after we add some solvent. For example, we will extract butyl ammonium cation pair with chloride and ion into chloroform from water. For this case, we have chloroform as organic solvent, and we have water as the heavy phase. That's a heavy phase. For this case, the K value is approximately 1.3. The K value is very low value. For this case, we can increase the K value, that's right, by add some ion pair. For this case, we add the sodium acetate. That's right, we add sodium acetate to the chloride ion in our system. If we add the sodium acetate in the chloride ion system, the K value will increase We increase about 100 times. As this, we can increase the efficiency of the attraction by adding some ion pair to our system. To our system. This is the example of counter ion for ion pair attraction, like for acetate. This acetic ion. Not high soluble in organic solvent. For that case, butylase, this is the chemical structure. In this case, more soluble in organic solvent than pure ion. If we use acetate, but we use acetate is low soluble in organic solvent, but butylase is high soluble in organic solvent. That if we would like to separate, we would like to make the ion pair of our system, we can add some butyrate or acetate to our system. And also we can add some this chemical, like this chemical, to the ion pair, and then we can increase the efficiency of the attraction. Okay, many solutes which we want to separate weak acid or base. For weak acid for base, that can be ionized in water. If you would like to extract for this system, the attraction of K value is vary with the change in pH. The change in pH, for example, by a weak acid can partially ionize in water, but it will not ionize in organic solvent. For weak acid, it can ionize in water, but not ionize in organic solvent. And then we can calculate the K value or the partition coefficient. Is it the lump of both ionized and unionized form? For K value is the unionized form. Divided by the ionized form plus the ionized form of hydrogen ion. From this equation, organic acid is ionized as RCCO minus and S ion. And then Ka, Ka is the associated constant. Associated constant is negative charge and positive charge divided by the unionized solution. This is the Ka. This is the K value. In practice, the hydrogen ion of the heavy phase it treats as the independent variable for that case. The subscript S it means the heavy phase. I mean our system of weak acid, something that is water system for that case. Okay, and then we combine these two equations and then we can relate K as Ki divided by some distance. By Ki is the ratio of acid in light phase and heavy phase. And then we combine these two equations, we get this expression as I read in Ki and K is a function of PS and pKa. PS and pKa, and if you take this off, you get Ki divided by K minus 1 for this K. And then you can calculate K value for the weak acid. And also this is for weak base. It's corresponding to like this weak acid with pKa. For weak base is pKb, something like this. It depends on the PS also for that case. And finally, how to separate is better or not, we can check this by the beta term. Beta term is expressed in this Ki of A divided by Ki of B. We compare between A and B solute. It also depends on Ka and Kb and hydrogen ion. For this equation show that K for weak acid decrease in organic solvent, we typically have low dielectric constant. In the length of Ki greater than K greater than 0. And also pH increase to value that exceed pKa. For the dielectric constant indicates the polarity of the system. Polarity of the system. And this show you the example of pKa. Like this for the acetic acid, formic acid, it's only one. But for amino acid is with the ion. Because in the amino acid, there are more than one group. Acid group, an acid group, and amide group, amino group, and also a group. When dissolved in water, we can ionize more than one ionic charge. something like that. Okay, more than one amino acid and more than one PK, PK1, PK2, and PKG. For the example, for the amino acid. And this for the peptide. PK and PA2 also. Is it another chemical? And I'll give you some example to calculate the effect of pH to the K value. Monoacidic sugar. For this case, we can extract from the water by using the hexanol as the organic solvent. And then the problem given you the K value for each pH. For example, like K value is 4.5 for pH 4 and 0.23 for pH 5.5. That's right. At the same temperature for this case. For this case, please estimate the value of K at pH 7.2. How to do this? That's right. We know pH 4, K 4.5, pH 5.5, K 0.23. The question is, what is the K value at pH 7.2? For this case, we can use the equation 14 like this. Because we can calculate K, because if you know Ki, pH, you know pKa, you know. You can solve for K, but for this example, we don't know Ki and K also. We need at least two equations to solve. Okay, for this case, we know PS. We know K. Okay, we know PS and we know K, but we don't know pKa and Ki. We know two conditions. PS4. That's right, PS4. And K is 4.5. That's right, we don't know Ki and pKa. And the second system, we know K equal to 0.23 and we know pH equal to 5.5. And then we don't know Ki and pKa. This is two equations, two unknown. We can solve. That's right. But it's nonlinear equation. After you solve nonlinear equation, you get pKa equal to 3.813. That's right. And Ka equal to 1.54 multiplied by 10 power minus 4 mole per liter. pKa equal to minus log K. And then you can solve for Ka. And the last one, Ki. Ki equal to 11.43. That's 11.43. And then you know Ki. You know pKa. You can substitute this term in the equation. That's why this constant. That's why Ki and pKa is constant. It's not depend on PS. Okay. And the general equation for this is K equal to Ki divided by 1 plus 10 power PS minus pKa. That's right. For this case, you know Ki. You know pKa. But for this question is what value of K at pH 7.2. You can substitute 7.2 and then you can solve for K. Okay. The final conclusion, you can see that when pH 7.2, K is 0.0047, pH 5.5, K is 0.23, and pH 4, K is 4.5. You can see that when you increase pressure, increase pH, K value will decrease. K value will decrease for this problem. In the next example, we will separate penicillin F. Sorry, we will separate the penicillin for the system water aminoacid. That's why we have the penicillin dissolved in water. Then we use aminoacid as the organic solvent to separate penicillin. For this case, we have penicillin two types, penicillin K and penicillin F. The K value for penicillin K is 150. Ki for penicillin F is 131. Right. The pKa for penicillin F, penicillin K is 2.77 and for penicillin F is 3.51. For this example, the penicillin is our desired product. View and extraction at pH 3 is a purer product than at pH 4. The question is we compare between pH at pH 3 and pH 4, which pH is better to separate the penicillin F? Penicillin F. Okay. For this case, you can use equation 13 and 14 to calculate K value, just like this. Ki divided by K minus 1 equal to 10 over PS minus PKA. That's why we know Ki for each PS. We know PKA for each PS. That's why you substitute Ki, PKA, and PS, you can solve for K. That's why. For example, right, for penicillin K, penicillin K at PS equal to 3, you substitute PS 3, pKa is 2.77, Ki is 215, and then you can solve K. You get K at pH3, that's right, for penicillin K, Kk is 80, and penicillin F is 100 for this case. That's right. And also for pH4, you substitute it, you get 12 and 32 for penicillin K and penicillin F respectively. Right. And also, how we compare this is can be separate better or not. You can compare this value by calculating the beta term. You can separate this. It's maybe A is the penicillin F, B is the penicillin K. You know Ki of penicillin F, you know Ki of penicillin K. You know Ka, right? You know Ka and hydrogen ion. Hydrogen ion you calculate from PS. It is mass log hydrogen ion, something like this. And then you know of it, and then substitute this. You can calculate beta is 1.3 at pH3 and 2.7 at pH4. That's clear because at pH4 the beta weight is higher than pH8. That means we can separate penicillin F at pH4 is fewer than at pH3, or it's easy to separate at pH4. Okay. I will stop the lecture now and we'll continue for the next lecture about the next example of the extraction. As I in the next extraction, we'll talk about the operation like batch operation, continuous operation.